Substances expand on heating and contract on cooling. An increase in the dimensions of a body due to an increase in its temperature is called thermal expansion. For example, the volume of the mercury in a mercury thermometer changes with a change in its temperature. Let's look at some examples of thermal expansion of substances that we come across in daily life. Rails are produced in fixed lengths, and fish plates are used to join them. The gaps provided between rails allow them to expand during summer. Expansion joints are provided while constructing bridges. When the temperature of any metallic body is increased, its length, surface area, and volume may increase. Expansion along length is defined as linear expansion. Expansion of the surface area of a solid is called areal expansion, and expansion of its volume is called volume expansion or cubical expansion. Let us consider a thin metal rod of length L at a temperature T. It is experimentally observed that the change in the length of the rod, delta L, is directly proportional to the change in its temperature, delta T, and also directly proportional to the initial length of the rod. Thus, we get equations 1 and 2. Combining equations 1 and 2, we get the expression delta L equal to the product of alpha L, L delta T, where alpha L is the proportionality constant called coefficient of linear expansion and is characteristic of the material of the rod. The fractional change in length delta L by L is equal to alpha L into delta T. Similarly, the fractional change in the area is experimentally found to be directly proportional to the change in the temperature. That is, delta A by A is equal to alpha A into delta T. That is, the fractional change in the area, delta A by A, is equal to alpha A into delta T, where alpha A is the coefficient of areal expansion. If the volume of a solid body is V and delta V is the change in volume for a change of temperature delta T, then delta V is equal to alpha V into delta T, where alpha V is called the coefficient of volume expansion. Though the coefficient of expansion is a characteristic of the substance, its value depends on its temperature. For many solids, expansion is analogous to photographic enlargement. For example, if a metallic sheet with identical holes, as shown, is heated, then the expansion is proportionate in all directions. The length and breadth of the sheet, radii of all the holes, and the distance between two holes all increase proportionately. Substances that expand at the same rate in all directions are called isotropic substances. For a perfect isotropic material, the coefficients of thermal expansion are related as alpha V equals to 3 alpha L and alpha A equals to 2 alpha L. Let's prove the identity by considering a cube of length L0. Its total surface area A0 equal to 6 L0 square and its volume V0 equal to L0 cube. When the temperature of the cube is increased by delta T, let the length of each side be increased by delta L. Therefore, the length of the side after expansion L equals to L naught plus delta L. Change in area delta A equals to 6 into L naught plus delta L whole square minus 6L naught square. This is equal to 6 into delta L square plus 2L naught delta L. The term delta L square can be ignored as the value is negligible. Then we get delta A is equal to 6 into 2L naught delta L. Now, by dividing delta A by A naught, we get 6 into 2L naught delta L by 6L naught square. On further simplification, we get alpha A equals to 2 alpha L. Let this be equation 1. Change in volume delta V equals to L naught plus delta L whole cube minus L naught cube. This is equal to L naught cube plus 3L naught square delta L plus 3L naught delta L square plus delta L cube minus L naught cube. The terms delta L square and delta L cube can be ignored as their values are negligible. Then we get delta V is equal to 3 into L naught square into delta L. Now by dividing delta V by V naught, we get 3 into L naught square delta L by L naught cube. On further simplifying, we get alpha V equals to 3 alpha L. Let this be equation 2. Let us now look at the expansion of solids at an atomic level. In a solid, the atoms are arranged in fixed positions. Expansion of a solid indicates that the average separation between the atoms is increased. As the temperature increases, the atoms vibrate with more vibrational energy, and the amplitude of vibrations also increase. The graph shown is the potential energy curve for two adjacent atoms in a solid as a function of their internuclear separation. Since the potential energy curve is an asymmetric curve, the average separation between atoms increases as temperature increases.